So welcome everyone for the afternoon session. Today we are joined by Devang from, I'm sorry, IISER-Mohali, and he will be talking about complex modeling with many data sets with BXA. So Devang, it's your turn.
Yeah, thank you. Thank you so much for inviting me. Hello everyone, I am Devang and I am a master student at IISER-Mohali in India. Today I will be talking about fitting complex models to many data sets within BXA. And yeah, so this is how I plan the talk to go. First, I'll start with the need for using many data sets in your analysis, then go on to describe how we are using BXA, and then I'll talk about some of the results from our ongoing work on heavily obscured AGNs, and then finally I will conclude with some of the tips and tricks that we found working to speed up the BXA fits and share some of the runtime analysis that we did. So the obvious question that you could ask just by looking at the title of this talk is that why would you need to use many data sets in your research in the first place? Well, many astrophysical phenomena produce the observables that are observed over a wide range of energies. So if you want to study, but the problem is that many of our instruments that we use to observe these sources have a limited bandwidth. So if you want to study a phenomena that ranges over wide energies, that what do? Then you combine data sets from many observatories with different wavelengths, different energy ranges. Another case would be when you want to do a multi-epoch study. In that case, it is highly unlikely that the same observatory would have observed a source in all the epochs, or even when the same observatory observes it in multiple epochs, you have different data sets. So, for example, in this recent study by Mislav, you see that these data sets, each epoch has different data sets represented by different colors. So that is one another case where you would have multiple data sets in your study. Another very interesting thing is when you see a sharp feature in your spectrum, for example, a cyclotron line if you are studying pulsars. And you want to make sure that this is a real feature from the source and not an artifact of your instrument. What do? You go to another instrument. So for example, in this plot, you have this new star, you observe some feature at around 20 keV. You go to another instrument, let's say LAX PC, and you see the same feature here again. Then you can be quite confident that this is indeed astrophysical in nature and not some artifact of your instrument. Finally, when you are calibrating different observatories, you would want to do a fit with only the calibration constant as a free parameter and data from different observatories that you are calibrating. So these are some of the cases that where you need to use multiple data sets. Now, why is BXA an ideal tool for this? I think you all have heard it enough times now, and you know that all these really good, really nice features provided by BXA in robust estimates and even in doing faster fits and getting better results, doing model comparisons and so on. One important thing is that when you have higher dimensional space, or when you have a complex model, the traditional methods like Liebenberg, Markov are become very unreliable. So that is why we are using BXA. Now coming to our work, I will first quickly introduce the unified model of AGN. This model was first proposed to explain the optical properties of AGNs. So narrow line region, broad line region, and so on. According to this model, AGN consists of a central engine, which is an accreting supermassive black hole, and it is surrounded by an obscuring material, which is known as obscuring torus. And what this model says is that different properties of AGN that you observe in optical can be explained by different orientations of this torus. But the problem comes when you try to extrapolate this model to X-ray. Some of the work have already shown that it is not really very easily extrapolated into X-ray. And when you many geometrical parameters related to this torus play important role in X-ray. So the unified model of AGN in X-ray is more complicated. Now, based on the column density of this torus, the AGNs are classified into different classes. One such class is Compton thick AGN, which is just to say that the column density is roughly greater than 1.5 into 10 power 24 per centimeter square. What is interesting about these sources is that previous work have already shown that a large portion of these type of AGNs make up cosmic X-ray background, but our understanding of these sources is very limited. Also, a large fraction of these sources are heavily obscured. But the problem when you have a heavily obscured AGNs, it is rarely X-ray bright. So whenever you get a X-ray bright heavily obscured AGN, it is a great opportunity to study the circum-nuclear environment. That is the properties of these torus, because the kind of the astrophysical phenomena that are characteristic of this torus are observed in X-ray. So that is exactly what we are doing with this source, NGC 2788A. This is an AGN galaxy, nearby AGN galaxy, SB type galaxy, that was identified as Compton thick AGN and reported in 70-month BAT survey. This particular source has some interesting properties. One is this very prominent ion line with equivalent width greater than 1 keV. This is interesting because this is a signature of a heavily obscured AGN. And then we also, from this work in 2017 and also from our work, we see that this source is relatively brighter in soft X-ray. So that is interesting. And we also see from two new star data, which were separated by 8 months, we see that there could be some variability in Compton hump as well. So that is also an interesting direction to study. Now what we want to do is we want to study the property of the obscurer, but there are many competing mechanisms which produce these observed fluxes. So what we do is we want to disentangle as many components as we can. So one great way of doing that is to expand your spectral range and try to fit characteristic feature of each component. So that is exactly what we are doing when we are using two epoch new star data and 3 more instruments. So that is why in our work we are using this multiple data sets. Now, once you have this data, what you would like to do is you would like to fit a model that can a torus model that can explain this data. So one such torus model is the Boras 2 model. This is the geometry of Boras 2 model. You have your source at the center, which is surrounded by a spherical sphere of obscuring sphere of uniform density with conical cutouts on either of the poles. And the angle of this cosine of this angle is known as covering factor. So you will see this guy in future as well. So just remember that cosine of this angle is this covering factor. Um, with this geometry, what we define a model which has these component. It has a line of sight component. It has the Boras component, and then it has a Thomson scattered radiation, which is the radiation that escapes from this from the open parts of this sphere. And we have a APEC component, which is just a dummy component to model all the soft X-ray flux. Now with this model, what we do is, this is the reprocess. Boras 2 basically is the reprocessed component, inverse Compton and K alpha line and so on. With this model, we do a spectral fitting to 4 datasets. And that is one of the new star dataset, Suzaku and BAT. And these are some of the preliminary results that we get. What we find is that this source has a very low scattered fraction. That is this Thomson scattered radiation, which escapes, if you remember, from here. And we could guess that if it has a very small scattered fraction, then it should have a large covering factor. And that is indeed what we get here. This is the covering factor. So indeed, we get large covering factor and small scattered fraction. We also find that our data at soft energies is not that good when you compare it to the new star, some of the new star data here. So, but using BXA, we were able to at least find some lower bounds and upper bounds on these components. And in the corner plot, you can see that this region, you can rule out this region of this parameter space. And another interesting thing is that you can see some of the slight bimodality already in this APEC component. So this could be a hint that you need to use 2 APEC component with 2 plasma temperatures, that is this KT. But we don't have that quality of spectrum at soft energy, so we cannot do that at this moment. Now, once you have fit, you can do various tests to check the goodness of fit. One test that we did was we picked 500 random points from the posterior generated by BXA, and then we use fake it to generate spectrum at those posterior points. And these gray lines are those 500 spectrum. The red line is the BXA fit. And from this spectrum, we see that where the bulk of new star data is well constrained, but the soft component is not that well constrained. And we can see sort of similar thing even in this plot. So on this plot, we show the C statistic, not C statistic, but the test statistic, which is C statistic for these 4 datasets and chi-square for this dataset. So these are fit statistics and fit statistic for these fake spectrum. So we see that these 2 new star and BAT are fairly well fit, but this Suzaku is overfit, and this data set is what is driving the overall fitting of the model. So again, if we have better soft coverage, then we would be able to constrain the soft spectrum better. But remember this plot will show up again. Now, if some of you have already tried fitting complex BXA models, you might have noticed that BXA takes a very long time. And especially so our ultimate aim is to compare various geometries of this torus. That means we need to do multiple fits with the different configurations. So in that case, this long runtime can add up very quickly. So that is why we had some tricks to speed up this process. First, obviously, I think all of you must have already tried this parallelization, use multiple cores. Another one is the frac remain argument in your solver.run function. This is by default set to 0.01, which takes long time. This is essentially tweaking the point where your fitting task stops. If you already know that all of your parameters are monomodal, then you can also set it to 0.5. But as we saw in our case, this is not applicable. So we have to do with the default setting. And the last one is the speed argument in solver.run. I'll elaborate more on this, but you can find all of this on tutorial page. I am sure all of you have already seen this, and even on Ultranest and BXA documentation. So this using this speed argument in solver.run, you can toggle between different type of samplers. What do I mean by that? Yeah, so the speed argument has three modes. One is the safe mode, which is default mode. This uses reactive nested sampler in BXA. And this is the most robust method, but it is also the slowest method. Then there is speed equal to auto mode, which switches to something known as step sampler. And in this mode, you determine the number of steps on the go. This is also quite slow method, but it is also it's a balance between the two. And finally, there is speed equal to integer mode, which switches to step sampler again, but with the number of steps that you specify. And this could be the fastest method, but there are some nuances that we'll talk about. So if you remember this plot from a couple of slides ago, what we see here is that I have run the same fit, but with two different settings, number of steps equal to 80 and number of steps equal to 20. What you see is BXA finds a similar fit irrespective of the number of steps. So that means you can get away with 20 steps if you want to only do a good fitting. But that is not the point of using BXA here. What we want to do is we want to compare models, and to compare models, we need base factor, which is calculated by BXA. And if you see in this plot, you have base factor for different values of speed equal to integer. So for this, so for these different integers, you have base factor which is different. And the black line is the fit with the speed equal to safe setting. What we want to do with this plot is that we want to ask, I don't want to run the safe speed equal to safe option. I want to use the speed equal to integer option. So what is the best that we can do and still be as close to safe as possible for the estimate of your base factor? So this is mentioned even in Ultranest documentation, and we also kind of find the similar results that what you want to do is you want to pick a value for a number of steps. So let's say you take 40 and then you do a fit, you double that value, you go to 80 and then you do a fit, and you see if the base factor for these two agrees within error bars. If it agrees, then you will be fairly close to the real, in quotes, real value of base factor. So that is kind of what we find, but this can break down in some cases. So for example, 30 and 60, it doesn't work. So what we would suggest is you do it for 3 steps. And the best part about this is that when you use step sampler, so for example, for these 4 data sets, we did n steps equal to 80, and we found that this takes 300 hours on single core. But the catch is that if you do the same fit, but with the step speed equal to safe, it will take 11,500 hours on single core. So there is a huge improvement when you use step samplers, especially when you have complex model and multiple data sets. So we would still suggest that you use step sampler, but in ideal case, if you have time and resources, you should do three fits. That's not. You should do 3 fits, and you can sometimes even get away with 2 fits. Finally, to summarize, we find that the unified model of AGN in X-ray is more complicated. That is shown by the relationship between scattered fraction and various other degeneracies in the spectrum. What we want to do next is we want to use different models of the torus and compare how the parameters of the torus vary between the models. This is especially important if you had attended yesterday's talk by Tathagata, where they show that the same different models can produce the same result. So it is really important to do fitting for different models and do kind of sanity check for various geometrical parameters. One possible solution would also be to get rid of this. This complexity arises because of the different assumptions that went into making these models of torus in the first place. For example, UX, Lumpy, and Boras, and so on. So one solution would be to do away with all that complication, which will be covered in Gabriel's talk tomorrow. So please attend that talk as well. And we would also want to expand this study to include more sources. And one really important thing that we want to do is get soft X-ray coverage and also high resolution spectrum from future missions as well. Yeah. So with that, thank you all for attending this talk. And if you have any questions and so on, then please.
We thank you for the amazing talk, and are there any questions from the audience in here? Any comments? No? Any questions online?
Hello.
Hey, Devang.
Hello.
So I've got a question. So you mentioned soft X-ray spectra. I was wondering, so what would high resolution spectra, what would they be able to do for the torus models?
Yeah, so if you have good soft X-ray coverage, then you would be able to disentangle the line of sight component and your torus component. So with that, you would be able to find how much of the reprocess component is because of the torus and how much is the line of sight. And also with soft X-ray, you would improve constraints on your APEC model, and consequently you would have better constraints on the other parameters as well.
Great, cool. Thank you very much.
Hello, this is Tathagata.
Hello. Yeah.
Yeah, so during the torus modeling using Boras, what kind of configurations did you choose? For example, is it a coupled Boras or an uncoupled one?
Yeah, so the results which I showed were for decoupled model.
Okay. Okay. And
So line of sight is decoupled from both.
okay. So NH-TOR and NH-LOS are
Yeah.
different, right?
Yes.
And for the other case, did you try a coupled one?
We tried coupled one, but I'm not sure if I have those results here.
Yeah, but just a
Yeah.
just a curiosity. Does
Yes.
the covering factor match for these two cases? Like how consistent is it? How different is it?
I think covering factor was consistent.
Mhm.
Yeah. But I'll have to go back and check.
Okay, no problem.
From Pravin on the chat, as a beginner question is related to basic reduction. When we do calibration of data like flaring, removing of AGN object from XMM, I follow the ABC guide, but I wanted to ask, is there any way we can be sure that we have correctly removed the flaring and not actual signal, or does this method vary object to object?
Yeah, I'm not sure because the kind of reduction which I did was using the default pipeline. So I think following ABC guide should be good enough.
I think also that might be a good one also for the Slack as well, because they're yeah, I wasn't sure. I don't think Devang's using XMM data. So yeah, if specifically for XMM, maybe try the Slack as well.
Hi, this is Johannes. I don't have a question. I just wanted to comment. I really liked your explanation of the step samplers, and you made it very clear the pros and cons, and really appreciated that contribution. Thanks.
Yeah, thank you.
Then if there are no other questions, we thank our speaker for today.
Thank you. Thank you.